what we're going to talk about is systemic countermeasures to improve highway safety, specifically 3 countermeasures we got across the state. Miles going to talk about the systemic approach itself, and Mike's going to jump into our friction efforts and thinking about how that we can use friction measurement to possibly in a systemic method. So I'm going to jump into the next slide. So let's start with an illustration that shows locations of fatal crashes in a particular county or particular time period. There's no discernible location or pattern in these crashes, which is common throughout our state. The randomness of fatal crashes makes it difficult to know where exactly to expend safety dollars to gain the largest return in crash prevention, which leads to this question. If fatal crashes are random, how do you prioritize? Well, I'm not sure if anyone knows the exact answer to this question, but a good safety program should utilize a systemic approach to safety, which we will talk about today. The systemic safety approach means an improvement that is widely implemented based on high-risk roadway features that are correlated with particular crash types rather than crash frequency. We've kind of hit that with the Mentimeter poll question, but the main concept is, the high-risk roadway features. It's basically that approach is where the practitioner focuses their attention on the roadway risk for a crash instead of a particular location. In other words, the roadway risk can be predictable because you're focusing on the pattern of similar crashes instead of the particular spot. In the pictures below, you can see various high-risk roadway features. We have a non-crash-worthy guardrail end treatment, a fixed object barn about 2 feet from the edge of pavement, and a drop-off around 4 inches. All these features could be addressed through a systemic based approach to safety, regardless of whether a crash has occurred in this location or not. This makes the systemic approach proactive instead of reactive. The concept of systemic safety has changed how folks have historically approached crash reduction. Typically, we identify locations where X amount of crashes occur in a short period of time at a particular spot. We invest X amount of dollars to improve the spot and then move on. The systemic approach uses the money you would have spent on this one spot to improve the crash performance along the whole corridor, region, or possibly state. This illustration shows the process generally utilized by a highway safety improvement program to identify projects and select countermeasures. For our state of Kentucky, rural roadway departure fatal crashes make up the largest percentage of fatalities. HSIP identified that rural 2-lane, greater than 50-mile-an-hour roadways to be the risk factor for roadway departure crashes. So the target crash type is roadway departures, and the risk factors are rural 2-lane, greater than 50-mile-an-hour roadways. HSIP then utilizes the Highway Safety Manual Network screening methodology to identify corridors that are rural 2 lanes with speed limits greater than 50 miles per hour, particularly ones that are experiencing more crashes than similar sites throughout the state. HSIP will then assign these corridors to a consultant to study crashes and select countermeasures to address the crash pattern, the features, the high-risk features. Then through the project development process, we often can prioritize certain corridors and move faster than others depending on the scope of the project and magnitude of the crash experience along the corridor. This process can be applied to any particular jurisdiction or region. One of the larger issues local governments have with achieving this process will be the data resources necessary to perform step 1 and someone with the knowledge to navigate them through the process. Luckily, we here in Kentucky have a great resource through our LTAP office that can help local governments with this process. For more information, reach out to them about local road safety plans if you are interested in looking at how to apply the systemic approach to safety to a local jurisdiction. So now that we've touched on the systemic approach, let's jump into the countermeasures. The 3 pictures contained on the slide represent 3 effective countermeasures that we have employed in the state and will be will be the three countermeasures I discussed today. The top left pictures of rumble strips. I think the majority of us in the state know what rumble strips are because we have so many on our roadways, but that wasn't always the case. The picture in the top right shows some applied horizontal alignment curve signing. We have, as a state, invested millions of dollars in new signing throughout the years, and there's still plenty of signing needs out there. Lastly, I want to point out the picture in the middle is of a 6-inch durable stripe. This is a relatively new countermeasure being implemented not only in our state, but the rest of the country. As I mentioned before, if you've driven our state, Kentucky, and not paid attention to the road, you'd most likely hit a solid rumble strip. As you can imagine, this countermeasure is effective at preventing roadway departure crashes. In fact, there are numerous crash modification factors that show a 44 to 64% reduction in head-on, opposite direction, and side swipe fatal injury crashes for centerline rumble strips, and a 13 to 51% reduction in single vehicle run off the road, fatal and injury crashes for shoulder rumbles, as shown in the slide. In Kentucky, we have had rumble strips installed as early as 2001. The first installation was centerline rumble strips on the Daniel Boone Parkway, now known as the Hal Rogers Parkway. These were installed as a response to several serious injury and fatal collisions, so mostly they're reactive. We continue kind of installing centerline rumbles on a reactive basis from time to time up until around 2008. This is about the time the systemic approach was kind of catching on. HSIP piloted about a couple hundred miles of centerline rumbles because they were easier to retrofit. And then around 2009, 2010, HSIP also piloted edgeline rumbles with newly resurfaced roadways. All those efforts, trial and errors, and et cetera, led to around 2012, centerline and shoulder rumbles had developed sepias, and around 2016, centerline, edgeline, and shoulder rumbles became standard applications when they were adopted in the standard drawings. So actually, rumble strips are now considered statewide as a systematic countermeasure. So, but it wasn't always the case, and it took a lot of effort, almost 15 years, to get to that point. Here's some snapshots of our standard drawings for various pavement widths. Some important widths to point out: edgeline only rumble strips are placed on roadways with a total pavement width of 22 feet. This will be wide enough to get two 10-foot lanes with 1 foot of shoulder on both sides. Moving down the chart, at 25 feet of total pavement width, you should install both centerline and edgeline rumbles, and the widths greater than 33 feet are widths for centerline and shoulder rumbles. These widths and thresholds were determined through trial and error and by looking at crash reductions for various pavement widths. So what about pavement widths less than 22 feet in total width? There's a standard drawing, and it's fairly new. A lot of people don't know about it. It's TPM 175 that provides guidance for striping on 2-lane roadways. Note 3 of this drawing states that the 2-lane roadways with pavement widths between 20 and 22 feet, edgeline rumble strips can be considered for installation. As shown in this note here, note 3. Here's a typical of what we have done in recent years, is convert some of the narrower pavement widths to the 22 foot range so that edgeline rumbles can be installed. The above typical shows conversion of 18-foot typical to a 20-foot typical by adding 1 foot of pavement to both sides. And here's the evaluation portion of what we looked at for some projects we've had implemented this kind of pavement widening to get those, not only get the width, but get the rumbles. As you can see in the before, we've had some not so good outcomes. And then after implementation, we've had reductions across the board, except for this one. Metcalf US 68, we did have an increase in B. It may have been some A's that have gone to B's or et cetera, but in general, we have had large reductions for those roadways. Now, this is just a naive kind of before and after. As soon as we get some more after data, we'll have our folks at KTC kind of run it through statistical gamut and make sure, what kind of crash reductions we got from this. But in general, we feel like these are pretty good wins, and we're going to keep doing this for other roadways in our state. Here's some more evaluation continued. We've had pretty good returns in crash reductions. We just looked at it through a benefit to cost. We're still getting like a 3-to-1 in 5 years on fatal and serious injury crashes, and almost 2-to-1 on total crashes. So still a very, very effective countermeasure. Switching gears to horizontal alignment signing. It's a relatively low-cost countermeasure. It can be systemically applied to horizontal curves to help prevent roadway departure crashes. The crash modification factors for horizontal alignment signing widely varies, but in general, you can expect anywhere around a 20 to 40% reduction in crashes as a result of horizontal curve signing. Because signing horizontal curves is relatively inexpensive, the return on investment is usually fairly large, which is why HSIP has invested significant dollars to horizontal alignment signing over the years. Something that people don't probably recognize is fluorescent yellow sheeting is another upgrade that's low cost, that you actually get a little bit more benefit than versus just a standard yellow. So we've implemented that as well. Here's Table 2C5 and the 2009 TCD. It determines the required amount of horizontal alignment signing for a particular curve. The difference between the posted speed limit and the advisory speed determines which signs are required, recommended, or should be used. Advisory speed plaques are required when the difference between the advisory speed and speed limit is 10 miles an hour or greater. Chevrons / large directional arrows are required when the difference between the advisory speed and speed limit is 15 miles an hour or greater. Here's an example of some well-done signing. I would like to point out that the difference between the advisory speed and speed limit is only 10 miles an hour. So the chevrons in this curve were optional. The practitioner who did the signing on this curve must have believed that the additional chevrons were warranted. There was possibly some crash history that made this curve stand out more than others. The other thing I'd just like to point out, signings can be pretty labor intensive. You have to go out and ball bank the curve, determine where the signs go, determine the advisory speed, issue the work, have someone install it, inspect it, etc. It's a lot of steps, but in recent years, HSIP has tried to help with that by acquiring some ball bank data. I hope some folks have used that in the presentation as well. Moving on to the last countermeasure, it's a fairly new one for us and a lot of the country, but it's the 6-inch durable striping. In 2019, we have a policy expanding 6-inch durable striping to the state primary route system. For asphalt pavements, thermoplastic should be used, and on concrete, retroflective tape is preferred material. Again, standard drawing TPM 175 provides further guidance for 2-lane roadways, particularly where there's consideration for 6-inch edge lines for pavement widths greater than 20 foot. They're not on the state primary route system. This is another systemic countermeasure. HSIP has invested a significant amount of dollars in the past few years. Particularly, we aimed at looking at roadways that were paved in the past 2 to 3 years since the policy was instated. I say this time frame because multiple layers of paint can prevent adequate adhesion of the thermoplastic, which will in turn require removing the existing stripes so that the adequate adhesion of the stripe can be attained. We also have some ongoing research on various striping materials and bead configurations. In particular, we're evaluating extruded thermoplastic, a multi-polymer stripe made by NS Flint, polyurea, and durable waterborne striping with standard, and evaluating those in combination with some different bead packages. Standard beads, there's a Missouri blend of beads that uses a little bit bigger beads. Utah blend uses the biggest beads. And then the 3M elements are also mixed in. KTC is Kentucky Transportation Center is leading these efforts. The picture to the right is of a stripe on the test deck. It is a 100 mil extruded thermoplastic stripe with a standard bead and 3M elements. The 3M elements kind of look like a poppy seed on the stripe. The extra thickness of the material helps to get better bead embedment, which in theory helps with retaining the bead and thus maintaining the retroflectivity. One of the larger enemies of bead embedment is the snowplow. This test deck is not recessed because we wanted to see how well these materials retain the beads after some snow plowing operations. This slide just shows, illustrates the importance of bead embedment. It not only helps with keeping the bead in place, but it helps with the retroflectivity itself. The illustration is from Ennis Flint, and it shows how headlights are retroflect back at us. If the bead has too much embedment, as shown in the far right, the light never gets reflected back. It just kind of goes back into the pavement, as shown in the illustration. If you have under embedment, it also kind of goes through the bead and never comes back to our headlights. And then they say, 55 to 66% of embedment gets your optimum retroflectivity. And so that's kind of the concept when we talk about a long life durable stripe. We not only do you want a material that can withstand traffic, we also make sure we have the right size bead to achieve embedment. Usually the beads that have the most retroflectivity are larger, so you need a thick stripe to obtain that embedment. And that's why we're evaluating all these various materials and stripes. Which goes back, and this is kind of my final slide here of why we're doing the switch to 6-inch durable. Other states have made a similar switch, and they have found that it's led to crash reductions. In particular, got this study from North Carolina that has evaluated the crash performance for durable striping for both 4 and 6-inch striping. They went kind of through the same process, used highly reflective beads and standard beads, but they showed reductions across the board with the change, mainly larger reductions with the 6-inch stripe. So that's why we made that change for the state primary routes. And that is the end of my slide, and Mike will take over.
All right, Nathan, if you could stop sharing your screen, I'll get mine going. All right, so as Nathan mentioned earlier, the systemic approach to safety is more of a proactive approach to safety than traditional previous methods. I'm going to discuss KYTC's pavement friction initiative, which I believe may end up becoming one of the most proactive safety initiatives we'll ever carry out. Hopefully by the end of the presentation, you'll see what I mean by that statement. Here are the topics I plan to talk about today. I'll start by explaining why we're so interested in pavement friction and go over the basics about pavement friction. I'll then give a high-level overview of the different methods in which pavement friction can be collected. One of the methods that's somewhat new in the US is called continuous pavement friction measurement. So I'll also discuss some of the advantages of collecting friction data in this manner. And then lastly, I'll talk about how we're going to use friction data to improve safety. So let's dig into the why. At the most basic level, the reason we want friction data is so that it can help us prevent transportation-related fatalities and serious injury, AKA the K and A crashes. There is a bit of a pun in AKA and KA crashes, by the way. The K and A severity crashes are estimated to have an annual economic impact to Kentuckians of over $10 billion. That's billion with a B. That's significant. When we dig into the crash data, we find that each year, 60 to 70% of Kentucky's fatalities are the result of roadway departure crashes, which are crashes that result of a vehicle leaving its lane of travel. In short, roadway departure crashes are generally either head-on, sideswipe opposite direction, or run off the road. All right, if we dig even further into the crash data, and we look at the 5-year period from January 2013 through December 2017, we found there's over 1,250 K&A crashes that were the result of roadway departure on wet pavement condition. That's an average of over 250 of this type of K&A crashes per year. The reason I point out roadway departure crashes occurring on wet pavement conditions is because friction likely has more importance on these crashes than any other crash type. Now, with all that in mind, if we can focus on improving friction across the roadway network so that we achieve even a modest 5% reduction in these K&A roadway departure crashes occurring on wet pavement, we could save the public over $28 million per year, but more importantly, save lives each and every year. And to me, that just means there's a huge opportunity if we can begin to make even small improvements in the pavement friction area. All right, now that we've talked a little bit about the why, let's talk about how friction works. At the most fundamental level, we need to understand there's two concepts to consider: friction demand and friction supply. The terms pretty much speak for themselves in that friction demand is the level of friction that's needed to safely perform braking, steering, and acceleration movements. In other words, as a car goes down the road, how much friction does that car demand from the pavement? Now, while friction supply is the level of friction a pavement can provide, friction supply can get a little tricky because it is based on a couple of different components, that being the micro texture and macro texture properties of the pavement surface, and some other things, weather conditions, things like that. But at the most basic level, micro texture and macro texture are important considerations. Now, if you're not familiar with these terms, here's a simple drawing of a pavement cross-section that hopefully helps to explain what these terms mean. The orange shapes, the orange shapes represent the aggregate within a pavement. The black shape represents the asphalt or cement, basically the glue that holds everything together. Microtexture is a measure of how rough or smooth the aggregate is, while macrotexture is a measure of the void space at the surface of a pavement. Microtexture is obviously an important component for determining a pavement's friction supply, because if the aggregate surface is too polished or too smooth, the pavement will be slick, especially when wet. Macrotexture is also an important component when we talk about a pavement's friction supply, especially under wet conditions, because these void spaces provide pathways for surface water to move into, allowing a car's tire to maintain contact with the pavement. You might be thinking, well, hey, doesn't the tread on a tire provide the pathways for surface water to move into so that the tire stays in contact? Well, the answer is yes. Tire tread does provide a lot of that void space needed for any surface water on a pavement to move into and allow that tire to stay in contact. But the more we've studied pavement friction, we're learning that a pavement needs to have a certain level of macro texture as well. That gives that surface water an alternative void space to move into. This is especially true on higher speed roadways, because at higher speeds, a tire is rolling across the surface water so quickly that the tire basically needs all the help it can get in trying to disperse water out of the way. Now, what I'm about to say is a little bit of an oversimplification, but when I hear microtexture, I think pavement grip. And when I hear macrotexture, I think pavement tread, because effectively that's what the macrotexture is kind of doing. It's acting like a tread, but on the pavement surface instead of the tire surface. The relationship between microtexture, macrotexture, and ultimately friction supply is a bit more complex than that. But hopefully this gives you kind of an idea of why we need to measure both microtexture and macrotexture. Let's talk a little bit about how friction data can be collected. The macrotexture component is collected by a laser-based measurement system that continuously measures every foot of pavement. There's several different laser-based systems out there, but they all basically operate the same. They mount to somewhere on a vehicle's frame or bumper, and then you can drive that vehicle down the road with the flow of traffic. The image on the right, it gives you a bit of an idea of what the laser is doing. The short and sweet is the laser is basically trying to take thousands of measurements of the peaks and valleys of a pavement surface and figure out what that sort of average or mean profile depth is. And us engineers are so creative that we name that resulting measurement mean profile depth. Of course, we love our acronyms too, so we've shortened it to MPD. So when you hear people talk about a pavement's MPD, that's what they're talking about. Now, because we're measuring the void space of a pavement surface, macro texture has to be collected when a pavement is dry. Any water or moisture on the roadway will throw off the reading, since there would be water taking up part of that void space. And it would just underreport what the macro texture really is. For micro texture, there are two primary ways it can be collected. The more common method that has been used in the US for quite a long time is the locked wheel skid trailer. A newer method that is just starting to be used in the US is continuous friction measurement. Here's a photo of a locked wheel skid trailer in action. Just like the name suggests, it's a trailer that's pulled by a pickup truck, usually a 1-ton pickup truck, because when you lock up the wheel on a skid trailer, you want something fairly heavy pulling it so you don't lose control and crash. How this method works is you identify a location you want to test. You get your truck up to speed, which standard test speed is 40 miles per hour. When you get right at the spot you're interested in, you basically hit a button. The left tire of the skid trailer locks up for 1 second and collects a reading. Now, when you're going 40 miles per hour, a 1 second test means you traveled just under 60 feet. So this also means that this type of friction measurement is basically a sample-based measurement. If you wanted to test another patch of pavement just slightly up or down from the first spot, you got to get your truck and trailer turned around, go back, well, turn around twice really, but get back up to test speed and then hope you hit the button at the right spot, that next spot you're interested in, which ultimately means the locked wheel skid trailer is not a good tool for measuring a lot of length down a roadway. You're basically just going to use it to spot check a roadway. All right, so here's a photo of a truck that's been designed and built to collect continuous friction measurement. Like I mentioned, the kind of a newer method that's starting to be used in the US. This truck drives down the roadway at a wide range of roadway speeds. It can go as slow as about 15 miles per hour and collect valid data, or it can go as fast as 55 miles per hour and collect valid data, which allows this truck to collect data basically with no traffic control, since it drives with the flow of traffic. The way this truck works is as it drives down the roadway, it pulls a rubber tire along the pavement, continuously measuring and recording data. Earlier, I mentioned that macro texture has to be collected when the pavement's dry. And when you're using either the locked wheel skid trailer or a truck like this, to collect the micro texture component, the pavement has to be wet. Because micro texture, we're interested in the value when the pavement's wet, since water surface will have, a wet surface will have less friction than a dry surface. That said, most of the trucks that, like this, that collect continuous friction data, they also do collect macro texture. You just have to strategically place the laser-based system in front of your water spray nozzle so that your macro texture readings occur before the pavement is wetted by a spray nozzle. In the next slide, I've got a video that kind of shows this particular truck in action. It's a slow-mo and close-up, but it's pretty interesting, cool video. Sucker to go in here. So you can imagine this occurring at much quicker speed, especially if you're going 55 miles per hour down the road. But that's the gist of what it does. Here's a still image of that video and showing the primary components on this truck. Just before the blue spray nozzle, you'll see a black box with a yellow sticker on it. This is the laser system that's collecting the macro texture data, which again, like I said, it has to occur when the pavement is dry. So that's why it's positioned right before the water nozzle. As you saw in the video, the blue nozzle is placing a film of water on the roadway, and directly behind this nozzle is the rubber tire that's collecting the microtexture data. It's a little hard to tell, but the rubber tire is turned inward 20 degrees. This causes the rubber tire to generate a resistive force. Now, you did see in the video the rubber tire was turning, but because the tire is not rolling straight, again, it's turned about 20 degrees inward. This generates a fair amount of resistive force. A sensor is constantly measuring this horizontal resistive force. There's also a hydraulic rod that applies a constant downward force on the rubber tire. This downward force is also known as a normal force, and another sensor is constantly measuring the normal force. Now, I point out these two forces because these are exactly the two forces that are used to calculate the coefficient of friction, which is ultimately what we're most interested in, because it's the coefficient of friction that gives us an indication of microtexture. The more microtexture a pavement has, the higher the coefficient of friction will be. So essentially, this truck is constantly measuring macrotexture and constantly calculating coefficient of friction for every foot of pavement as it drives along the roadway. It's a pretty incredible machine when you stop and think about it. Which this kind of leads us into the discussion about the advantages of collecting continuous pavement friction. This image shows the results of continuous friction measurements, as well as results from a locked wheel skid trailer over a 6-mile stretch of roadway. The red line is continuous macro texture data. The blue line is continuous micro texture data. The small yellow boxes are micro texture data from a locked wheel skid trailer that collected from spot checking 7 locations in the same wheel path the continuous friction measurement was collected in. If we zoom in on the blue and yellow boxes, we see that the yellow boxes and blue line are consistent. I'm going to pause right here and explain that because the locked wheel skid trailer is dragging a completely locked rubber tire across pavement, and a continuous friction measuring device does not lock up its rubber tire, the friction values reported from each device are different. Generally, the continuous friction measurement value will be slightly higher than the locked wheel value. So when I say the blue line and yellow boxes are consistent, please realize I'm not saying that these values are the same. As generally speaking, these two values will never be the same. But these two values should follow a similar trend, with the yellow boxes generally being just below the blue line. The big difference I want to point out is the amount of data that we get with the continuous friction measurement. Because the blue line is data that was collected continuously along the pavement, we're able to pinpoint locations where microtexture drops way down, as highlighted by the larger red boxes. The only way you can identify these types of low frictions with a locked wheel skid trailer is by having a bit of luck and hoping that you happen to spot check the location with lowest friction. Unfortunately, hope is not a good strategy. And as I said earlier, the locked wheel skid trailer measures about 60 feet at a time. So when we do use this device, it's unlikely that we'll ever know with any kind of confidence if we've truly pinpointed the spots with lowest friction along a roadway. Now, that said, we do know that curves and approaches to intersections are the locations that tend to lose friction quicker than most other sites along the roadway. So we could try to use the locked wheel to strategically spot check curves and approaches to intersections, but there's also a lot of risk involved with locking up the wheel of any trailer you're pulling when traveling around a curve or approaching an intersection. As doing that, locking that trailer wheel up could cause the driver to lose control. So realistically, the locked wheel skid trailer is just not really good at collecting data at the locations we're most interested in. All of this ultimately means that continuous friction measurement gives us two big advantages. One advantage is being able to collect friction data on any roadway feature, whether it's a curve, intersection, ramp, or just a plain old tangent. The other advantage is obtaining a continuous stream of data, which allows us to accurately pinpoint which roadways have low friction values and where those low points are located. All right, so now that we have all this friction data, what do we do with it? Let's go back to the basics and talk about friction demand versus friction supply. The collected friction data is obviously the friction supply side of this relationship. But how do we know the friction demand part? Well, like most things in engineering, the answer begins with it depends. And in this case, it depends on quite a few things. But speed and a wide variety of roadway geometry are the key players in what dictates friction demand. Now, we can't know every possible speed that drivers are going to be taking as they approach the different parts of the roadway network. And we can't know the exact geometry of every foot of pavement. So to start to understand friction demand, we first need to slice up the roadway network into similar categories like curves, grades, intersections, merge points, and tangents. And again, we're very inventive, so we call these site categories. But once we've identified which pieces of pavement belong to which site category, we can then look at the average crash rates for different coefficient of friction values over the thousands of sites we've collected data for. What we see when we begin to do this exercise is that there will be some level of friction that as you go lower, the average crash rate will start to go up exponentially. Kind of this location on the graph where that curve starts to bend upward is considered the friction demand level, or at least that's the friction demand level we're very interested in, since the risk of a crash goes up quite a bit once you go below that level. The graph here is a made-up example of what we might see after grouping the data for all tangent sections along two-lane roadways. We would repeat this process for all the different site categories until we have a friction demand level for each site category. Here is another made-up example of what the final set of friction demand levels might look like for a wide variety of site categories. The reason this example and the previous slide example are made up is because we're still in the early stages of analyzing the thousands and thousands of miles of friction data that we've been collecting for the past year. So I simply don't have any results to share just yet. But when we looked at what some of the other countries across the world have been doing with continuous friction measurement, their friction demand levels tend to follow or have this same kind of variance. Tangent sections on the higher class roadways, such as interstates and multi-lane divided roads, tend to have the lowest friction demand levels, while relatively small radius curves along undivided roadways and approaches to high-speed intersections tend to have the highest friction demand levels, which when you think about it kind of makes sense, because I mentioned that friction demand occurs due to steering, braking, and acceleration maneuvers. So it's kind of no surprise that these spots demand more friction. And just the exercise on the previous slide helps us ascertain what those demand levels are. All right, so once we determine friction demand levels, the next step is identifying and prioritizing locations for possible friction improvement treatment. Obviously, the highest priorities are going to be locations where the friction supply is much less than friction demand. Like everything in life, we've got a certain budget, but if we still have funding after developing projects for those highest priority sites, next up would be any remaining sites where the friction supply is less than the friction demand, just maybe not as greatly less than as the higher priority sites. And then after that, we still have available funding. We'll start considering sites where the friction supply is really close to the friction demand. Of course, as we continue to measure, monitor, and essentially manage pavement friction, our ultimate goal is going to be to keep the friction supply greater than the friction demand at all sites, or at least as many sites as possible. Will that be a challenge? Absolutely. But if we can achieve that or get close to achieving that year after year, I'm positive we'll see significantly fewer skid-related crashes. In fact, the country of New Zealand, they've been doing continuous friction measurement and going through this process for over 20 years now. And they estimate that they've seen a 40% reduction in skid-related crashes. If we can achieve a similar 40% reduction in Kentucky, we estimate that would save the public over $224 million per year in crash costs. So the potential is huge. We're really excited about this and hoping that this is going to be a major proactive way to improve safety in Kentucky. So that's the end of my presentation. We can open it up for questions now.
Yes, thank you, Mike. Wanted to thank our speakers, thank Mr. Zwala, the Transportation Cabinet, and the entire Lifesavers Planning Committee for making this webinar series happen. And thanks to all of you for joining us.